The electrostatic energy of Z protons uniformly distributed throughout a spherical nucleus of radius r. So that means what? That this is a nucleus and this is the radius r. So the electrostatic energy which is there is given by this formula, which is E is equal to 3 by 5 into Z into Z minus 1, okay, 4 pi epsilon naught r into E square, which is mentioned there. Now we can clearly see that here Z and Z minus 1. Okay, now for different atoms, for different elements, Z is going to be different. Okay, Z varies. So therefore the electrostatic energy also varies for different elements. Now the measured masses of the neutron are respectively, okay, given the radii of both nitrogen and oxygen nuclei are the same. So radius is same but Z is different, so therefore the electrostatic energy will also be different for oxygen and nitrogen. Okay, now 1 U, that is the atomic mass unit, is equal to 931.5 mega electron volt per C square, and E square is this much. Assuming that the difference between the binding energies is purely due to the electrostatic energy, the radius of either of the nuclei is. So first let us calculate the difference in binding energy. Okay, so binding energy of nitrogen. So for this, first calculate the delta M, mass defect of nitrogen, so which is 15. Okay, so if you see, nitrogen is composed of 7 protons and 8 neutrons. Okay, so ideally it should have been, the mass should have been 7 into proton is 1.007825 and neutron is plus 8 into 1.008665. okay, this should be the ideally, but it is not this much. So how much is nitrogen? It is 15.000109. so therefore now we have to calculate the entire thing. Okay, so I am doing it by calculator, but it is not recommended to do by calculator. So 7 into 1.007825 plus 8 into 1.008665 minus 15.000109. So this becomes 0.123986. This is the delta M of nitrogen. So therefore the binding energy of nitrogen is 0.123986 into 931.5 mega electron volt divided by C square into C square. Okay, so this much. So into 931.5, that is 115.5 mega electron volt. Now we calculate the binding energy of oxygen. So this is going to be, so there are 8 protons and 8 neutrons, so therefore 8 into 1.008665 plus 8 into 1.007825 minus 15.003065. okay, one thing here, oxygen is 8 and 15, so there are only 7 neutrons. So we'll use 7 neutrons here. So this is going to be 7 into 1.008665 plus 8 into 1.007825 minus 15 into 0.003065, not 15 into, minus 15.003065. So this is equal to 0.12019. So therefore the binding energy, so this is the delta M for oxygen. So therefore the binding energy of oxygen is going to be, okay, into 931.5, which is 111.956985 mega electron volts. Okay, so basically we write 96 only and we are neglecting it. So 111.96 mega electron volt. Okay, so now what is the difference? If you see, that was 115.5 and it is almost 112. So therefore the difference in binding energy is equal to, let us calculate. So this is 115.5 minus 111.96, which is equal to minus 111.96, which is equal to 3.54 mega electron volt. Now this is going to be the now this is going to account for what? The potential energy. Okay, the difference. So therefore let us calculate this. So delta E, that is the difference in electrostatic energy, is going to be 3 by 5 into 1 by 4 pi epsilon naught. Okay, so E square by, this is already given, 1.44 mega electron volt femtometer, okay, into 1 by R. Now Z into Z minus 1. So for oxygen it's going to be 8 into 7, which is 56, and for nitrogen it's going to be 7 into 6, which is 42. Okay, now this is going to be 3.54 mega electron volt. So this is gone, this is gone. So R becomes 3.54 into 5 divided by 3 into 1.44 into 56 minus 42 is 14. This is 1 by R. Okay, so R is going to be 3 into 1.44 into 14 divided by 3.54 into 5. So let us do 3 into 1.44 into 14 divided by 3.54 into 5, which is 3.417 femtometer, which is 3.42 femtometer. Okay, so therefore the answer is the C part. Okay, so again we recapitulate. So therefore first we calculate the difference in the binding energy, and then as it is said that the difference in binding energy is due to the difference in the electrostatic energy, so therefore we use delta E here also. Okay, thank you.